can you actually write on this? Do these markers work?
Can you write on it?
Yeah. Might be helpful in a couple places to draw on top of the presentation. But I don't know. Do these work?
I don't know. I've never used them. I think it's an electronic
Yeah.
board. We had a couple minutes more.
Okay.
Welcome to the first of our seminar series. This is a joint seminar series sponsored by the Institute for Energy Efficiency and also by the Center for Energy Efficient Materials. And before we get into our talk today, I just want to point out to you that next week, David Lee from our geology department will be giving an overview of climate modeling. David's a highly respected expert in that field. He's going to give us an update on what's happening with climate modeling and climate change. I think you'll find it very, very interesting. Today, we're very happy to have Nathan Stoddard here with us from Solar World. And Nathan is going to talk about silicon, especially the very challenging question of how you grow silicon in large quantities with very high quality and purity, particularly for photovoltaic applications. Nathan, currently chief scientist at Solar World, has also worked at EP Solar, where he developed much of the technology that he'll describe to you today. Nathan?
All right. Thanks for the introduction and for the invitation to come today. So I will be talking about freezing silicon. I do represent Solar World. I'm not the chief scientist, but I am clearly a very important scientist. So, yeah, I'll take that. Okay, so I'm going to go over kind of design parameters that you want for photovoltaic materials, some of the distinctive properties of silicon that make it an interesting and challenging material to deal with. Talk about the problem from the point of view of an ideal final result, which can be a useful tool. And then look at past approaches rather briefly, and then what's going on in current R&D, both within Solar World and a couple of the other things that are happening in the industry, and then look towards the future. So if you look at the general photovoltaic problem, first you have to look at your energy supply. And so if you look at the broad spectrum of light coming from the sun, only a certain amount of it gets through. And so there's a gap here. So this, I should say, is absorption. And there's an absorption gap in the atmosphere in the visible range, and our eyes appreciate that. And then there's also one in the radio range. And so in terms of terrestrial astronomy, there's really, there's light telescopes and then there's radio telescopes. And the radio wavelengths aren't tremendously useful because the energy in them is kind of way off on the low scale. Within the visible range here, we have a nice mix of energy, starting at about 0.4 microns and then moving out into the infrared. But if you weight the emission with the photon energy, this is kind of the spectrum you get. And so we want something that's going to capture really that range of energy and convert it into electricity. What are we going to use to do this? You need something that has an electron separation energy that's roughly equivalent to the energy ranges that we were talking about. So we need something, first of all, that has an energy gap, and that's going to wipe out really your metallic materials because there's just no energy gap there to exploit. Our noble gases are also pretty useless here because it just takes so much energy to separate that first electron. And so we end up with this kind of intermetallics here. These guys, especially at the high end, are pretty good candidates all on their own as covalently bonded materials. And of course, you can also use useful combinations of columns 3 and 5, which obviously the gallium nitride people have a lot to do with. In terms of absorbing the energy, you can also even go out to 2,6 materials, and sometimes people even sneak copper in there as a dope in materials like SIGs. So here's a brief list of semiconductors with the band gap at room temperature, and then the corresponding to that band gap, the maximum wavelength that they can absorb. Most of these are crystalline. Many of them are diamond structure or zinc blend. Some are hexagonal. So of these many options here, why would one move towards silicon? Well, in the electronics industry, there's a couple basic answers to that. It's relatively easy to grow. It's just a problem of freezing, and we're going to get to that. It's conceptually extremely simple. You melt it, and you freeze it, and you're done. It's easy to dope, and you can do so with simple thermal processes. It's plentiful, but that's really not important for electronics. But the thing for electronics is that it has a stable oxide dielectric. Silicon dioxide is a wonderful combo player with silicon to make a lot of the early devices and have a passivated surface and to do so in a relatively easy manner. For solar, the answer is a little different. The band gap is near optimal. It's 1.1 eV. The optimum is 1.4 for a single layer photovoltaic material. It's chemically stable and it's non-toxic, so it's going to be able to sit out in a field for 25 years and not have any problems. Again, it's easy to grow, relatively easy to process, and here natural abundance becomes important because instead of making ever smaller devices, we want to cover ever larger areas of land with photovoltaic materials. And so we're going to need enough silicon or other absorber material to do that. So let's talk a little bit about abundance in the Earth's crust. Silicon is way up there at 27.7%. These other kind of good candidate materials here typically have at least one element that is in quite low quantities, and especially copper, indium, gallium diselenide has both indium and selenium at about 0.05 ppm, and the other one that people talk about a lot is cadmium telluride, and tellurium is at 0.005 ppm of the Earth's crust. And primarily our sources right now are coming from the waste streams of other major materials processing, so typically like zinc mining or other kinds of mining activities, from which these are a side product. And so there's an open question: do we have enough of these materials? And I'm not going to try to answer that here, but the answer for silicon is for sure. So things going against silicon. Number one is the indirect band gap. 1.1 eV is not direct, and if you compare silicon with the direct band gap material, you need 100 times more in thickness just in order to capture the light. So you're going to need a lot more of the material to make something useful. A single band gap of course, does not absorb photons that are less than 1.1 eV. So we are, in fact, cutting out the infrared part of the spectrum. And this is a full 30% of the solar energy that we're more or less throwing away by drawing our single band gap cutoff line here. Also, we can't get more than 1.1 eV because anything higher than that that's absorbed falls down to the basic 1.1 eV level, and the extra energy is lost in heat. And so all of this up here is also lost, and that's about 30% as well. So our maximum theoretical efficiency for this silicon perfect device would be around 29%, which isn't great. And there's a lot of good research going on for materials that try to have a much higher maximum efficiency, either by stacking materials together or using quantum confinement effects, that kind of thing. So that's some of the things I talk about here. There's organic materials can continue to have one of the highest potential efficiencies and one of the lowest actual efficiencies. But I'm not giving up on them yet, so we'll see. In the meantime, how do you make high purity silicon? You start with quartz, coke, and wood chips, and so you have silicon dioxide, and then you have carbon sources to reduce the silicon dioxide down to silicon. They have these, this is a person here, these gigantic furnaces that do this, and they come down with 3 electrodes here, graphite electrodes, and typically this big bed here would be filled with these raw materials that come in on rail cars and then are brought in on big tracks and just dumped in here. And they heat this dome in here to something like 4,000 to 5,000 degrees, at which point you get gaseous reactions. You strip the oxygen off of the silicon, and the gases go up as carbon monoxide, carbon dioxide, and the silicon, as the only liquid in the system, comes down and runs out into these. And at this point, you're talking about a material that's about $3 per kilogram, maybe 99.9% pure if you're doing everything right. To turn this into a high purity material, they go through a chemical distillation process. So first you react the silicon with chlorine and hydrogen to make trichlorosilane, which is a liquid, and then they purify it by a simple distillation process. Of course, I say it's simple, but it's vastly expensive and takes a long time to build. But it works extremely well, and you can see the number of 9s here that I wrote out is actually real. I mean, this is not just me holding the 9 button down. This is actually attainable, and here over here, it's a little hard to read, but these are actually actual impurity values of purified polysilicon in picograms per gram, or parts per trillion by weight. And the biggest number on this chart, these are detection limits here, but so the biggest actual detected number is probably 20 here, 20 parts per trillion, the highest. So you can take this trichlorosilane, you can turn it into polycrystalline rods, solid rods, and that's the basis for this impurity analysis here. You can also try to deposit it directly into wafers, and there's various research in that direction. But the problem is that it's pretty slow. Silicon growth from vapor is a high temperature and a slow process. And so if you're trying to build up this absorber that's at least 30 microns thick, preferably more like 100 microns thick, it's just going to take quite a long time. So what's more typically done is either you make BBs in a reactor, and somebody asked me today about spheral silicon. They take these little BBs and try to make something directly out of them. But right now the traditional route is to make BBs or rods that then get melted down again. Well, I say again, but it's the first time it's been liquid since the metallurgical phase, but you have to melt it down and then you can crystallize something useful. So I want to go back just a second. Why do we need such high purity silicon? It goes back to this indirect band gap. We need a lot of material in order to absorb the full spectrum. Once that spectrum is absorbed, those electrons and holes that have been created somewhere deep in this bulk need to live long enough to take a random walk all the way up to the emitter level. Emitter is typically at the top of the device. It's the most convenient and generally accepted way to do it, because most of the light is still absorbed up at the top, but you have this long trail of IR light that needs the full bulk to get absorbed. And this stuff here, it's going to take a while. It needs to live. If you're thinking of other optoelectronic devices, this stuff needs to live for up to 100 microseconds or a millisecond, which is an extremely long time for this electron-hole pair. And in that time, it can't meet anything in the silicon where it's going to recombine. And that includes impurities, and that includes crystal defects. And so that's why you need the purity. You can't have anything in that bulk above the parts per billion level, especially on metals, because you're going to lose all of those electrons and holes that you've worked so hard to convert. Okay. So getting back to this idea, so we have a problem. We want to create a photovoltaic material. We can talk about what the ideal solution to this problem would be. So let's start with version 1. The most ideal thing I can think of would be to go directly from this highly purified trichlorosilane or silane precursor directly into a substrate. So just make a large area absorber straight away. You would want this process to be low temperature. You'd need a fast deposition, and like I said, at least 25 microns, preferably thicker than that. And you'd want, again, large grain or single crystal layers, because you can't have a lot of recombination going on. And the dislocation density also has to be low. And at the same time, you would also put your doping layers on, probably through the same kind of deposition as you're doing for the main substrate. And ideally, this would be on a glass substrate. But this is problematic because glass does not provide the crystallinity you need, and it's very limiting from a thermal point of view to deposit directly onto glass, and then from whatever temperature you're at, come back down to room temperature and have a lot of stress. So people are working on this. There's a couple companies out there that are trying to do this and have some kind of clever ways, but so far there's nothing that really looks like it's going to break through. Version 2 then, if we go slightly less on the ideality scale, we would go from a gas to this feedstock that we solidify very quickly that's still high purity. Then we'd melt that, but we'd take the melt and make wafers directly out of the melt. And then these wafers would be the right thickness and the right size to process into photovoltaic devices, and we'd go on. So this would be thin, it would be flat for processing reasons. It would be pulled quickly from the melt, so you'd need at least a millimeter per second of pull rate. So let's say you're pulling a 5 or 6 inch wafer. If you're pulling a millimeter per second, then you're going to get a wafer out every 2.5 minutes or so at this rate. And that's still kind of slow. You'd really like it to be faster than that. Again, you do want to have a single crystal structure, and you want to have low residual stress, and you want to really avoid contacts with foreign materials from a purity point of view. It becomes an issue, and it actually ends up in some impurities going back to a structure issue too, because if you're growing this crystal and you get the right kinds of impurities in there, that it's going to more or less trash your crystal structure. So there's people working on this too. And in fact, I worked at a company working on this for about a year. It was a startup in Massachusetts. There's a couple historical guys that I'll go through that did this in production and were relatively competitive, but both of the main players there have dropped out of the market in the last year and a half time frame. So I would say that there doesn't look like a big disruptive technology coming here either. So let's go a little further down on the ideality scale. And so now we're going to take our pure gas, we're going to turn it into a solid feedstock, we're going to melt that feedstock, and now we're going to solidify a large block, and then we're going to take that block and we're going to cut it into thin wafers. So the cutting part is definitely a step down on the ideality scale, and we'll get back to that later. But what would we want from this? We would want fast, large area crystal growth, ideally a minimal melt volume for safety reasons. I'll talk about that later. Single crystal is, again, highly desired. You want high purity, but especially low oxygen. So we've really kind of come down here, and you have to kind of recognize that. But the interesting thing is that in straight kind of head-to-head competition, from research that's been going on for more than 30 years now, this is kind of by far the winner in the current. So let's say that you want to make a 6x6 wafer, 6x6 wafer, and it's going to be 25 microns. You'd like to have that done probably in the same time scale as here, within a minute or two. And of course you can help yourself if you can parallelize that process. But that's a rough idea. Okay, so I'm not going to address really the people working on this top part, but I will talk to what has been done, again, working from the melt to a solid state. So what is it that makes freezing silicon so fun? There's a few things. First of all, it's really pretty high temperature, 1,412 degrees or so to melt silicon. It's hot enough to give you a sunburn if you're looking at it, okay? And a company I worked with in Massachusetts, they had these funny, appropriate for the Northeast, kind of lobster pot sort of designs. And the silicon was melted at the bottom of them. There's just a quartz plate sitting over the top, and it's got argon flushing in there. But you could look in there, and it would start to burn your face just to look at it. So we had these gold masks that we would wear. Electrical conductivity goes through a gigantic range. The highly pure stuff has basically no dopants in it, and so it's generally greater than 1,000 ohm centimeters at room temperature. By the time that you heat it up to the melting point as a solid, it's done its semiconductor thing and gotten much more conductive, so you're down at like 0.003, and then the instant that it melts from going from solid to liquid, it jumps again from 0.003 ohm centimeters down to 8 times 10 to the minus 5 ohm centimeters, which is really metallic. So it's really going from a kind of resistive metal to a conductive metal, and it's doing so in that phase change process. And that also has consequences for the optical properties. The solid has a relatively high emissivity and gives off a lot of energy. The liquid is more metallic, and it's not very emissive at all. We'll talk about what that means for us later. Another interesting thing about silicon, it's like water. The liquid is denser than the solid. So if you had a glass of silicon, the ice cubes would be floating at the top, right? And this is different from most metals. Almost all metals have the solid heavier, and so things like casting are simpler. Viscosity is similar to water. It really runs around. The surface tension is pretty high, though. It's more similar to mercury, and so it runs around, but it does so kind of balled up. The heat of fusion is extremely high for silicon. It's 50 kilojoules per mole, and just to put that into context, it takes slightly more energy to go from solid at 1412 to liquid at 1412 than it did to get you from 0 up to 1412. So you've only done half of your work by the time you're up at the melting temperature. And of course, we've talked about this indirect band gap, which is really driving a lot of the things that we're doing in making the silicon into a solar material. Constraints and challenges. Silicon's extremely reactive. It's more or less the universal solvent. If you put almost anything into it, it's going to be reacted one way or another. I talked about this emissivity change. It also tends to solidify dendritically if given the chance, and that's partially driven by this by the heat of fusion. It will emit a lot of heat when it is solidifying, and so if it's searching for new cold places, it's pushing heat out to the side. It has to move out in front of it, so you get these long, skinny crystals that like to grow. And then it is at room temperature up to 600. It's an ideal brittle solid, and so it does have thermal stress and dislocation formation to worry about. So what's been done historically? In the 50s, you had the beginnings of silicon Czochralski and float zone. You had dislocation-free crystals in 58. In the 1960s, there was this kind of co-development of purer feedstock silicon and bigger and better Czochralski silicon pulling. I'll talk more about that later. And then in the 70s and 80s, partially with this initial research into solar that came about, you had a number of new growth methods coming out. And then recently, we're talking more about commercial implementation of things that were just kind of lab projects, and then a couple new things that have come about. So we'll get to those later. And just one more time on this sawing issue. Sawing blocks into wafers waste silicon. The wafer thickness today is typically 160 to 190 microns. It used to be much thicker than that, and sawing wasn't quite so much of an issue. But as the wafers have gotten thinner, the kerf width, which is the wire plus the carbide particles around it, is now basically the same or even perhaps slightly more than the wafer you're getting out of it. So all of the silicon that was formerly here is turned into relatively unrecoverable dust. So it's a pretty wasteful way to make wafers. So we're going to start, motivated by that, we're going to start by on the freezing silicon methods that try to go directly to a wafer format. This is string ribbon. It was originated by Ted Cizek at NREL and also Ellie Sachs, who's got the company that I worked for in Massachusetts. And the way it works is that you bring two filaments of string, typically graphite or silicon carbide, and you bring it up through the bottom. There's two small penetrations in the bottom of the crucible here into a melt of silicon, and then you start with a seed crystal of some sort between these two that then pulls up a meniscus. And so here's a picture of the process actually happening. It's a little dark, but here's the wafer coming out of this small pot of silicon. The liquid down here looks relatively dark, again, because it's low emissivity. And then the bright line here is where it's solidified, and so it's more emissive, and then it cools down relatively quickly. The tricky thing about this process is that you're trying to extract your heat more or less back up the wafer, but at the same time you're moving the wafer up, and these two vectors being parallel more or less limits the speed that you can grow to the rate at which you can extract heat. And so you have to try to cool more and more aggressively right down close to the liquid itself. And Here's a temperature versus height graph. If you want to freeze at even 0.3 millimeters per second, which is, again, a factor of 3 lower than my kind of target value, you need a change of temperature with height of more than 500 kelvins per centimeter. And that's pretty extreme. It leads to relatively high stress. And so over here you have a scan of dislocation density, and then this is also a lifetime scan. And you can see that not only are there very bad areas, but there are actually pretty good areas too. But the presence of the bad areas really pulls down the whole wafer performance. So a company was founded that did this in relatively large scale and closed its doors last year. But it's a really interesting. What's that? The standard that they worked with for so long was 3 inches wide, and just towards the end of the life of that company, they were trying to do full 6 inches. But it was really the 3-inch wide width that kind of directed their whole company's evolution, because it was smaller than standard wafers, which even when they started were 5 inches. And so all of the standard cell and module processing was based on a 5-inch wafer. And they couldn't sell their stuff directly to other people to process it. And so they had to come up with their own equipment for processing these 3-inch wafers. And then they had to come up with their own module stuff too. And so instead of just being a relatively simple crystal growing company, they turned into this fully integrated cell and module company, which put a lot of tax on research and development there, and also on capital expenses when they wanted to expand. So the main innovation here, though, is managing this surface tension and being able to pull this very thin wafer between these two filaments. And it's really a nice process. Another process came about around the same time that instead of pulling up a meniscus with filaments, more or less used a pressure situation to push liquid up through a die and then to pull the wafer up, no strings attached. And in this case, this figure is actually a figure from Kyocera, and this is for alumina, you'll notice. And alumina is actually made by this technique. But it was commercialized for silicon, and the main thing that they did that was really quite smart is they were able to eliminate their edge effects. There's a lot of instability around these edges of the wafers here. And they were able to eliminate that by making tubes. And they made octagonal and 9-sided and even 10-sided tubes where each side of the tube would then be cut into a wafer width. But the edge effects that you'd get here would be non-existent because it would be cut out in this little angle. Schott commercialized this, and again, they filed for bankruptcy earlier this year. One of the main problems they had, in addition to everything else, was they could not get a single crystal out of the process, and the kind of gravitational pulling up of this caused thermal stress as well, and so there'd be a lot of residual stress in the wafers, which ended up being a problem. But it was a pretty cool process. I mean, seeing these big octagons, and they'd be 20 feet high. But the other problem that they had were all these container materials. This was generally graphite, same as this. There are containers here. The container is graphite, so that's putting quite a lot of carbon into your melt, and that while electronically that's kind of okay, it does cause other problems with silicon carbide formation. So here's the last wafer making that we're going to talk about. And this is called horizontal sheet silicon. It's been tried 3 or 4 different times in slightly different ways. This one had this liquid on top here and the substrate kind of pulling out below it and freezing a solid sheet like that. This one here, this is a little broken, but it came down with things from the top that would try to solidify a sheet from the top and then pull it out and then release it. And the releasing is really the tricky part. This one here was kind of a molded wafer process where they stabilized the edge. One of the trickiest things they had here is that if you don't stabilize the edges, the surface tension of the silicon pulls the wafer up into this little ball, and it becomes perfectly useless. So they had to find a way to keep the silicon attached at the edges so that it wouldn't ball up, but at the same time such that the whole wafer would release off of the substrate when they were done. This one is I think maybe the most interesting. Here you have this bowl of liquid silicon, and again there is a container here that is going to have some kind of impurities associated with it, but what you try to do is you try to crystallize this sheet of silicon off the edge of it, and in the ideal case this should be a single crystal as well. A paper was actually published just very recently in Journal of Crystal Growth looking at this from a theoretical point of view. I know there's at least one company that has a small research effort on this, again in Massachusetts, but I've not heard good things about their progress. The tricky thing here is that the tip of this growth, on the whole, the idea here is that you're pulling your heat out upwards while you're pulling the wafer sideways. So you've separated the crystal growth and heat extraction directions compared with the two earlier methods we saw, which are going to be necessarily slow. So here, at least theoretically, you should be able to just pull the stuff at up to a meter per minute off the side, and since you're extracting your heat vertically, you don't have to worry about this problem we had earlier. But the tricky thing is that somewhere at the tip here, at some scale, that tip is going to have some kind of curvature to it. And at that very tip, you're going to have that same problem of your heat extraction and your growth being closer to the same. So the question is, can this kind of point here be confined in space and not be pulling back and forth and trying to jog, because that's going to lead to instability and stress. If this point here is changing, then this whole angle is changing, and you're going to end up with a kind of wavy wafer. I tried a particular solution to this at my last company, and the problem that I had was that I couldn't extract enough heat from this little area here, because in order to propagate the single crystal, you have to have the heat extracting out through the crystal, and right at the tip here, what we talked about all the time was, well, we needed a cold laser. We needed something that could focus coldness on the edge of that the same way a laser can focus heat, and we couldn't come up with a viable way to do that. We looked into that, yeah. We looked into that, and we did a couple different attempts, and in every case, it wasn't confined enough, and it would end up cooling the melt up here, and then once this melt gets cooled, then you start getting dendrites growing out into the melt, because there's essentially a well of supercooling out here, and the silicon just jumps right into that. So I'm not saying it can't be done, but I wasn't able to do it, at least in the year that I spent trying. So, okay. One more. Last one, I promise. So this is the company I was working for, 1366. And it's mostly here for this picture, which I'm very grateful that they had. In this case, it was, I think, an Argentinian graphic designer put together, because they wanted to have a way to kind of advertise their process, which is trying to solve the same problem, making large wafers fast directly from the melt, but they didn't want to say anything about how they're doing it, and I still can't say anything about how they're doing it. And so what they did is they were trying to explain this to some people in government. They got some government funding, and it was a group of, I think, senators' aides or something like that in the room, and they're explaining it. And they explained it as simply as they possibly could, and they said, no, you got to make it simpler. And so in a moment of inspiration, the CEO said, okay, imagine a vast pond lake of silicon, liquid silicon, and down comes this eagle. And he swoops down, and he skims this wafer off the top of the pond, and then pulls it up. And that's how they make their wafer. And the guys were like, yes, that is it. You've got the right level of technical content now. And so here we have the eagle clutching the wafer. So they've got their own process, and maybe they'll be saying something public about it. All right, so wrapping up, I think no wafer sawing losses, small melt volumes. The drawbacks, really, dimensional qualities are very hard to get. Sawing wafers creates extremely flat, extremely uniform wafers, and really, we've spoiled our cell guys by giving them these nice cut wafers. And the cell device people don't want to deal with anything that has a little bit of ripples to it or anything like that. And I mean, in truth, it does cause problems, especially with wafer breakage. So I think the best potential breakout is still figuring out some sort of low-angle sheet silicon, and perhaps somebody will look at a solution to that. Look out for cold lasers. If you see those, give me a call. Okay, so moving on to bulk silicon. This is the float zone method, and I won't say too much about it. It's completely awesome. You start with these highly pure polysilicon rods, so they've got tiny little grains, and you basically have just a single electromagnetic coil, just a single turn, and there's a hole in it, maybe about this size. And what you do is you bring the silicon down, and you have to do a little bit of preheating to get the silicon to couple inductively to the high frequency RF magnetic field. But once it does, it becomes kind of self-sustaining. It gets conductive enough, and you get actual melting of the silicon. And then what you do is you bring a seed crystal up from the bottom. This is a nice picture here. You bring a seed crystal up, and you touch the end of the melt, which is just kind of dripping off here, to the seed crystal, and then you start basically pulling down, and you keep the heat coming in from the coil here, and the amount of melting that you're doing, you keep that balanced with the rate that you're pulling down, and you can make this thing wider. You can see here that it started thin, and then they grew it wider in a typical necking process, and then once you reach your goal diameter, you can just keep this thing steady all the way. So you can see here is the edges of a float zone ingot that's in the middle of the growth. And here again is the high emissivity solid, and then the boundary to the low emissivity liquid that's sitting in a pool on top of it. And you get a lot of good things happening. It's a fast process. It's very high purity. There's no contact with any foreign materials. Single crystal, absolutely. It does still get you a circular ingot. There's a group in Germany that's been trying to make square-ish float zone, and they've gotten kind of square, but they can't do it any bigger than 4 inches. And the main drawback here is the feedstock you need. You need polysilicon rods, but they have to be grown slowly. Normal polysilicon feedstock has these kind of cracks and a kind of cauliflower shape to it. And the problem with that is that this induction here creates an electrical current that travels around the outside of the silicon. And if there's a crack, then the induction is not going to jump the gap there. Essentially, it's going to shrink in and go inside of that crack. And so the melting is not going to get out to the edges. You're going to get this kind of hollowing out of the middle. And in the extreme case, they talk about basically these long unmelted icicles ending up left behind. And as you're pushing it down, eventually that's going to contact the heater, and that's going to form an arc, and you're going to have a lot of trouble with your process. So they like crack-free polysilicon rods, and those are generally at least twice as expensive as the standard silicon feedstock. Whoops. Okay, CZ silicon. This is a very simple process invented by Mr. Jan Czochralski. And basically, you just dip a crystal down into a pool of silicon, and then you start pulling up, and you match the crystallization that's happening, the pulling rate with the crystallization rate, and you get a meniscus here. And if you want a smaller ingot, you pull faster. If you want a bigger ingot, you pull slower. And it's very well done at this point. It's really kind of an engineering triumph, I think, that this is done in a high volume manufacturing. It's a finicky process. It would really like to have one person sitting next to each grower and really watching it the whole time. But they've done great things, and I really only knew about the manufacturing side of this once I joined Solar World, because that's the main crystallization we do in the Oregon factory. But they grow these 2-meter-long crystals and at a very high yield and with a very tight diameter control too. So, yeah. So the process is conceptually simple, but controlling it is considerably hard. And there's been a lot of work, just hundreds of papers that have gone into thermal simulations and convective simulations and magnetic. Really every side of this thing has been looked at. And still you can't really run a control program that is really in control of the whole thing. It runs in feedback, and there's a little bit of positive feedback, I think, that happens where you have to really oversteer it to keep it in diameter control. So they do a pretty good job with that. But the bottom line is that you're still growing around 1 millimeter per minute, and you're growing just one ingot at a time, and that ingot has just one wafer cross section in it. So from a mass throughput point of view, the speed is relatively fast, but you're only getting 2.7 kilograms per hour. When I'm talking about the next process, multicrystalline, you can grow 25 to even 36 cross sections in one crystal. And so as you're solidifying that interface, even though the linear rate is much slower, the area is much larger, and so you can get much higher throughput rates, which really cuts down on a lot of costs. Okay. So this is the last of the existing things, and then I'll get into some new stuff on the casting side, or on the bulk crystalline side. So this is multicrystalline casting, and this has been around for 30 years already. And it's also conceptually very simple. You get a box, in this case a quartz crucible. Today the standard is a little less than a meter square and maybe half a meter high. You fill it full of chunks of polysilicon, just stack them in there. You put it inside the furnace. You melt all that down to a liquid level that's typically maybe 2/3 of the height of the crucible. And then you start extracting heat from the bottom, and you just grow a relatively planar interface straight up. There's no attempt at controlling crystallization, so you get random nucleation of small crystals at the bottom. You get competition between those crystals early on, and then you get these fairly steady columnar crystals, typically somewhere between maybe 5 millimeters and 20 millimeters in size. Here's a typical wafer. That's a 5-inch wafer for context. And when you make a solar cell and a module, you definitely get lower efficiency than CZ, based largely on structural defects, grain boundaries and dislocations, but also on purity. In the case of the CZ, you're lifting the ingot up out of the melt, and the ingot itself isn't actually touching anything. The liquid is, but there's a high segregation that happens where almost every impurity, really with the exception of boron and oxygen, has a much higher solubility in the liquid than it does in the solid. So even if you have it in the liquid, it's going to stay in the liquid. And as you're pulling your ingot up, the ingot's going to be much higher purity than the feedstock it started from. In the case of casting, you get that same effect. The impurities do move towards the top, but you have a problem as well, because once this stuff is frozen, let's say up to this level, it's still very hot. It's still 1,200 degrees or so, at least, maybe 1,300. And the diffusion from these foreign materials, the crucible and the crucible release coating, is very aggressive at those temperatures. And so you have basically the entire process time while you're solidifying this that impurities diffuse in. And these impurities end up cutting down on the lifetime of the material. So this is a minority carrier lifetime. And in this case here, you can see red is bad and blue is good. And so you get stuff coming from the bottom and in from the sides, and it ends up being a bad thing. And another thing that happens with impurities is that you get carbon, which is kind of from the furnace atmosphere, and then you get nitrogen as well from this release coating, and they move up to the top, but typically form little solid particles, silicon carbide, silicon nitride, and a lot of that ends up at the top. You can see this huge raft of material here. This is all silicon carbide, silicon nitride, and in addition to that, this whole thing is covered in a thin crust of silicon carbide too. And there's some of these silicon nitride needles, and then in dark here, there's silicon carbide kind of platelets and starbursts. So interesting and simple, but kind of riddled with defects. So next, electromagnetic casting. This is an interesting one. What you have, this was invented again by Ted Cizek at NREL, who was developed and actually commercialized at SUMCO in Japan, and they made up to 2-ton ingots. And this is how they did it. They have an electromagnetic cold crucible here. So this is water-cooled copper, and it forms a square cavity. And in the center of this square cavity, they start out with a graphite base that's more or less all the way up here. They melt the silicon that they put in here, and because of an electromagnetic repulsion that happens between the current that's running in the silicon and the current that's running in the heater, you get this kind of bubble-shaped liquid up here. And because this is water-cooled, it's also aggressively cooling the liquid next to it. And so you get this kind of a liquid-solid interface. So you have, once you start growing this thing, you have this big solid ingot, and you have this cup of melt on top. And so you keep dropping solid granules from the top. They keep melting, and then you keep solidifying as you go down. The it's a really cool method. And the craziest thing is that they went as far because they wanted this to be a true semi-continuous process. So what they did is they grew this thing, and as it was still growing up here, they devised a way to cut an ingot out on the bottom. And so they'd cut this out, and then they'd go and support this part, and then keep pulling that down, and eventually they'd cut the next section. And to do that while you've got liquid silicon up here, in this electromagnetic repulsion thing, I think was just kind of crazy. But the problem that you get is this high thermal gradient, and it causes random nucleation of grains, and you get really very small grains, really very high thermal stresses, and electrically this stuff is a disaster. So it was indeed commercialized, based mostly on the ability to make these gigantic ingots and to do it relatively cheaply, but the efficiency on the solar cells never really got to where they needed to be. So now we come to what I worked on at BP Solar. This is a technique that I developed, and basically it starts with all the same things as the multicrystalline case. Same feedstock, same furnace, same crucible. And the difference is that you place a seed crystal at the bottom here. And instead of just melting everything down, you have to keep the seed crystal somewhat cooled while you melt everything else on top of it. And then you increase your heat flux at the bottom, and then you grow your ingot straight up, but you grow it from that seed crystal. And in this way, you can make ingots that are really substantially single crystalline, but made in the same time and with the same parallelism as a multicrystalline product. And so there's a wafer, cell, nice module here. And so we named this mono squared when I was at BP Solar. And really the key innovation is the idea of seeding over a large surface area. In most of the other bulk techniques that we talked about, people like to start with a small seed crystal, and they dip it into the liquid, and that dipping process always creates a number of dislocations. And if you try to just grow an ingot up from this dipped seed, it's going to have dislocations all through it, and they're going to propagate and multiply, and you're going to end up with a multicrystalline product very quickly. So what they do is they grow this long neck, and because, especially with a 100 crystal direction, dislocations all grow along diagonal planes. And so as they're growing down the neck, they eventually terminate at the neck wall. And once they all terminate, then you've got a single crystal with no dislocations left. And so then they grow it out and grow the long crystal. But what we were able to show here is that if you preheat your seed crystal properly, if you introduce the liquid in a more or less quasi-equilibrium state, that you can get seeding where there are no thermal shock dislocations. This just doesn't happen. And as a result, you get no necking process needed. So now I can't say that this is a fully dislocation-free seeding process, honestly, because I never took the time to really check whether everything was dislocation-free. But what I can say is that the few dislocations that do come in here do not act as crystal killers the way they do in CZ and float zone. And the reason is that the thermal gradient is significantly different. We're dealing with a large, flat interface. There's not the same curvature, and there's not the same gradients that you have to hold in these other processes. So that was really the key thing. And the other kind of counterintuitive thing is that if you think about our glass of ice water, in this case, the ice has to stay at the bottom while we do this melting on top of it and then grow our ingot. And so I think that was also a non-intuitive thing, but going back to the ice water analogy, if you keep the bottom of your glass cold enough, then water can't get under the ice. to float it up. And if water can't get under there, then the ice will stay on the bottom. So in this case, we do a similar thing. We keep the bottom of the crucible cold. Any liquid that does want to get under there gets frozen and doesn't undermine you and float the seed up. So how are we doing on time? Okay. So here's some ingots that we made. And here you can see that there is actually, in this case, a dislocation cascade. But this doesn't come from seeding. This comes from silicon carbide or silicon nitride particles, which were also endemic to the multicrystalline process. And we have problems with them here too. If a large enough particle hits the interface, it will lead to dislocation multiplication and eventually multicrystallinity. But the good thing we've got going is instead of growing a 2 meter long crystal, we're just trying to grow a third of a meter or something like this. And then we're done. And we've grown 25 of these things in parallel. So we can tolerate this to some extent in a way that CZ can't. All right. So the bottom line is that this material gives you a cell efficiency entitlement. And you can, with the right cell process, go from something that would normally be 16% efficient up to something that's even 19 or 20% efficient from a solar cell point of view. And that's really a big deal in photovoltaics. This process we worked on at BP Solar. It's been largely copied, and even though we got a really pretty good patent on it, it took 5 years for that patent to grant. And so that only happened last year. And in the meantime, everybody else picked up the patent application and said, oh, this is an interesting thing. Let's give it a try. So there's estimates that up to 25% of the PV market could be using this process by 2016. But in everybody else picking it up, I think a number of them don't quite have it right. And so there's still a question of whether the entity that now owns all that IP will be able to derive some value from it by providing their expertise and that kind of thing. So that's an open question. We can talk about it after the talk if you're interested. So here's the drawbacks of our bulk silicon. I think I've gone over it all. It's a hard to freeze material, and really it comes down to a couple things. The large heat of fusion, you have to pull a lot of heat out of there, and you have to maintain a gradient so that it doesn't decay into these dendritic guys. The surface tension ends up being a major sticking point for wafer techniques, and it is very susceptible to thermal stress because the temperature is so high. Okay, so I've got some new things here. This is a patent application that I filed a while ago, but together with Dave Carlson, who was the chief scientist at the time with BP Solar. And this is based on top-down solidification. And so instead of growing bottoms up in this kind of upside-down ice situation, why not start with the seed at the top and grow down into the crucible? And there's a couple of good things that you could do there. The problem that you get to is the silicon expansion. It's going to expand as it freezes. So if you seal off this top layer here, you're going to build up pressure as you solidify more and more. And eventually that pressure is going to be big enough probably to fracture your crucible. And then that's going to make a mess. So we suggested a pipe here to outlet the pressure. In reality, this is fairly difficult to implement. But a group in Japan has picked up on this, and they've done something very clever. They've essentially set a 4-wall bottomless crucible inside a larger crucible, and they've managed to get the silicon not to leak out that bottom seal. And so they start top seeding, they grow it down, and as the pressure gets high enough, it simply raises the wall enough for the liquid to squirt out, and then it sets itself back down, reseals, and then they continue growing, and they end up burping silicon at the bottom a couple times. But it's actually, kind of clever. And the silicon pressure never gets too high. Another way we talked about doing it was more or less gripping a seed from the top and letting it kind of float on top here, trying to grow it straight down, and but not touch the sides, such that at the end it's kind of like CZ, except instead of pulling the ingot clear, you're allowing the ingot to grow down into the crucible and over a much larger area, trying to use this idea of large area seeding. And so another group in Japan has taken this up, but they've hit this problem that the silicon really wants to be circular, and that's a surface tension issue. I don't know if they'll get over it or not. I'm going to skip that. This I've got in there just for Paul, because Paul and I worked for a couple years on this project. It was really the idea of taking the mono-squared technique to the next level and overcoming some of the limitations of the multi-process. So we designed this 3-chamber system where you'd introduce solid, you'd melt it, you'd then dock up to a solidification station, you'd pour your silicon down onto the seed, and it eliminated a lot of the problems. It ended up being a really big project, but I'm not sure that anything's going to be done with the result. So the last one, again, is what I'm working on now. And of course, I can't talk about it that much. I put up a watch this space sign, so maybe I can come back in a year or two and tell you what I'm working on. But I think it is another next step. I think there is absolutely the ability to dislodge incumbent technologies. They've got a lead, they've got a large installed manufacturing base, but we can still do better than the techniques that are currently ruling the industry. And this is just an idea. If you want, you can look up this patent and see what they're doing. Okay, and then the last thing is that I think you can cleave silicon wafers. And you're going to just have to call me crazy for that one and talk to me later, because we're out of time. So thanks, and
we're running late. Let's have just one or two quick questions. I got one about if you look, Nathan, at the total energy required to grow by these various techniques, how does that compare to the energy yield as a photovoltaic device? What are you talking about? Are you talking about the equivalent of a few months or
yeah.
a year or what?
Yeah, the energy payback time is something that people watch. It's now under 2 years. It's generally about a year and a half you pay yourself back, and getting better, I have to say. The energy density is very high, especially in these furnaces. I calculated it's something like having 500 sticks of dynamite inside the furnace, the total amount of energy that it takes to melt 400 kilos of silicon. So.
Second question is, what about recycling? Is there any value in that, or is the starting material so inexpensive compared to the total cost that it's not worthwhile?
You mean end-of-life modules?
Yeah, or even taking the, when you're sawing ingots, taking the waste material and using that?
Well, the stuff that's cut off of, like, to make a circle into a square, that stuff is absolutely recycled. Most of the places that you can do that, it is done. We went through a silicon shortage a couple years ago, and during this time, people did everything they possibly could to use every bit of silicon, and tried very hard on the silicon kerf issue too to clean that up. But it gets rubbed with iron wire, and it's tiny little particles interspersed in oil with silicon carbide. It's really quite a problem to get anything useful out of that, and it does end up rivaling the feedstock. So.
Okay, this question,
I just had a quick question. So you have this big seed mono-squared process that you grow from. Is that something that you just slice off of a previous one you make, or do you actually have to go to a much higher purity and
Yeah. So we did develop a recycling process for seeds. In order to make the first one, we had to start from smaller single crystals available from like the Czochralski process and assemble a larger seed. There's a patent application on that, and a lot went into that as well. It's an easy way to get a lot of defects in if you do it wrong. So.
What does the market prefer, the cheap polycrystalline one or?
That's a question that's gone back and forth a lot. If you asked me a year and a half ago, it would have been the cheapest one, which was generally multi. And that's cheap on a dollars per watt generated basis. Multi-crystal or polycrystal product is still the cheaper option today, but today the market seems to prefer the higher performance. And I think that's going to be temporary. I think in the end it will be the best dollars per watt that you're getting.
Is graphite the only material that's really used in those large melt processes as a crucible?
No, the standard for these large processes is a quartz crucible, and the silicon nitride silicon nitride coating on the inside of that. People have looked at graphite, especially because the quartz is a single-use crucible. It goes through a phase transformation, and on cool down, it fractures, and you can't use it again. So you just pull it away from the ingot, which is more convenient than trying to pull them apart. But people have looked at reusable crucibles and haven't yet found a good. But that's a possibility for cost savings in the future.
One last question.
So with all this new research, do you see the price of solar panels coming down?
Absolutely.
By when?
Yeah.
By how much?
So if you look at prices 2 to 3 years ago, for panels, it was around $250 per watt. So a panel might have been at that point 220 watts or so. So a panel would be like $600. Today, that same panel would produce about 10% more energy, and it would cost around $250. So we've seen a huge drop just in the last couple of years. If you look at the historical curve, it's more or less exponential, and I would expect that to continue for at least another 5 years. So we're at $1 per watt now. I think we could easily get down to 70 cents a watt within the decade.
Where do we need to be to break even without subsidies?
Well, the Sunshot Initiative from the Department of Energy is aimed at 50 cents a watt per for modules. But the answer to your question is that it varies by area. The sunnier area that you're in, the easier it is to justify the cost of solar. And for a true subsidy-free competition, I think 50 cents a watt is a good target, but I think for modules, yeah. They talk about $1 per watt for the system. But I
Actually, 2015, I think, isn't it? The Sunshine Program?
2020 maybe?
2020?
I hope it's 2020. Because we're not going to make it by 2015.